Deep in Tibet, the Yarlung Tsangpo cuts through some of the most dramatic mountains on Earth. Born high on the Tibetan plateau, this enormous river begins a journey through the heart of the Himalayas. Then the river reaches the legendary Great Bend, plunging through one of the deepest and most spectacular gorges on Earth. Here, the river loses more than 2,000 meters across roughly 50 kilometers, creating extraordinary hydropower potential. And now, China is attempting to harness this immense natural energy through one of the world's most ambitious hydropower projects. Across the vast Tibetan plateau, the Yarlung Tsangpo begins as a high-altitude river surrounded by an immense, rugged landscape. As it travels eastward, the river enters increasingly dramatic terrain, where enormous mountains rise thousands of meters above the water. The river then enters a spectacular Himalayan gorge, where towering cliffs and powerful currents create an extraordinary natural environment. The combination of enormous elevation change and flowing water gives this region some of the greatest untapped hydropower potential on Earth. But turning that natural potential into electricity means building massive infrastructure in one of the most remote places on the planet. Near Namcha Barwa, the Yarlung Tsangpo makes its dramatic turn through a landscape dominated by enormous Himalayan peaks. From above, the Great Bend reveals just how extraordinary this river is, winding through a canyon surrounded by towering mountains. As the valley narrows, the river accelerates, transforming immense elevation into powerful, fast-moving water. Before construction, engineers had to understand the region's complex geology, steep terrain, water flows, and extraordinary environmental conditions. For engineers, this combination represents an enormous opportunity, but also one of the greatest construction challenges imaginable.
According to the elevation data, this route minimizes tunneling.
Yes, but what about the impact on the downstream areas during peak season?
Rather than relying on one conventional dam, the project is planned as a cascade of 5 major hydropower stations along the river. Much of the engineering challenge lies underground, with enormous tunnels and power facilities planned deep inside the Himalayan mountains. In July 2025, construction officially began, turning decades of planning into one of China's most ambitious infrastructure projects. The project is expected to cost around 1.2 trillion yuan, making its scale almost impossible to comprehend. Before massive structures can rise, engineers must first build roads and access routes through this remote Himalayan terrain. Deep underground, powerful drilling machines are cutting through solid mountain rock to create the enormous tunnels required for the project. Every meter presents challenges because engineers must work through complex rock formations, fractures, water seepage, and extreme underground pressure. Excavated rock must then be removed, transported, and managed across steep mountain roads using fleets of heavy construction machinery. Here, modern engineering is confronting a landscape so enormous that even the largest machines appear tiny beside the Himalayas. The plant system will use 5 hydropower stations, arranged along the river to capture its extraordinary elevation drop. Water can be guided through engineered tunnels towards turbines, converting the river's gravitational energy into electricity. Deep beneath the mountains, enormous underground powerhouses will house turbines and generators designed for continuous operation. Inside these machines, the force of moving water spins turbines, while generators transform that motion into electrical power. When completed, the project is planned to generate around 300 billion kilowatt-hours of electricity every year. To build this project, engineers must excavate an enormous network of tunnels and underground chambers deep beneath the Himalayas. During construction, carefully engineered diversion systems can temporarily guide river water around areas where major structures are being built. Inside these passages, massive volumes of water must be controlled while engineers protect the surrounding rock and reinforce the tunnel walls. Thousands of workers and machines will construct reinforced concrete structures capable of enduring enormous hydraulic forces. Eventually, These structures will stand directly beside one of the world's most powerful mountain rivers, transforming its natural energy into electricity. Construction is taking place in a remote Himalayan environment where steep mountains, thin air, and difficult access add another layer of complexity. Because a project of this scale requires continuous progress, construction crews and machinery can operate around the clock. Sudden rain, powerful winds, cold temperatures, and rapidly changing mountain weather can make construction conditions extremely demanding. Even transporting heavy equipment is a major engineering task, requiring carefully planned routes through narrow and difficult mountain terrain. Standing beside these mountains, workers reveal the true scale of the project and just how enormous the Himalayan landscape really is. Once completed, the project is planned to generate roughly 300 billion kilowatt-hours of electricity every year. Its planned annual generation would surpass the Three Gorges Dam, making this project unprecedented in China's hydropower ambitions. To deliver that electricity, massive transmission infrastructure will be required to carry power from this remote Himalayan region toward distant demand centers. The electricity could support China's growing energy demand while providing a major source of low-carbon power. For China, the Yarlung Tsangpo represents an extraordinary combination of water, elevation, and energy potential in a single river system. But this river is more than a source of energy. It flows through one of the Himalayas' most fragile and diverse ecosystems. Large hydropower infrastructure can alter natural river conditions, potentially affecting water flow, habitats, and downstream ecological processes. The project also lies in a region shaped by powerful geological forces, making seismic safety a critical engineering consideration. Engineers must carefully study rock formations, fractures, groundwater, and seismic conditions before constructing massive underground structures. And the biggest question extends beyond China's borders. How could such a massive project influence the river farther downstream? After leaving Tibet, the river enters India's Arunachal Pradesh, where it is known as the Siang. Farther downstream, the Siang becomes the Brahmaputra, spreading across the vast plains of Assam. Across this river basin, millions of people depend on the Brahmaputra for farming, fishing, transport, and livelihoods. The river continues southward, carrying enormous volumes of water and sediment toward the low-lying plains of Bangladesh. In Bangladesh, the Brahmaputra is known as the Jamuna, forming one of the country's most important and dynamic river systems. The central question is whether such a massive project could significantly influence water conditions downstream. During the monsoon, rainfall can dramatically increase river flows across the entire Brahmaputra basin. For communities living on the floodplain, changes in river flow and water management are matters of serious concern. But the opposite question is also important. Could changes in seasonal flows affect water availability during drier months? Scientists continue studying these questions because the project's long-term effects on flow, sediment, and ecosystems remain uncertain. India is closely watching the project because the Brahmaputra is a vital transboundary river flowing into its northeastern region. China says the project is designed primarily for hydropower generation and has emphasized that its development will follow environmental and safety requirements. But the Himalayas are geologically active, so understanding earthquake hazards is essential when designing massive underground infrastructure. Engineers must account for geological fractures, groundwater, rock stability, and seismic forces throughout the construction process. Because the river crosses national borders, engineering decisions upstream can become questions of water security, diplomacy, and regional trust. In Bangladesh, the Jamuna supports farming, fishing, transportation, and millions of people living across its floodplains. The river also carries enormous amounts of sediment from the Himalayas, constantly reshaping its channels and banks. Sandbars appear, riverbanks erode, and channels shift, making the Brahmaputra Jamuna one of the world's most dynamic river systems. Meanwhile, high in the Himalayas, construction is progressing toward a project that could fundamentally transform this river's energy potential. But what the river will ultimately look like after the project is completed remains one of the most important unanswered questions. With an estimated investment of around 1.2 trillion yuan, this project represents an extraordinary financial commitment to hydropower. Building at this scale in the Himalayas means overcoming extreme terrain, complex geology, difficult logistics, and enormous technical challenges. The project represents a remarkable achievement in engineering, but it also raises difficult questions about the river and the environment. How will downstream ecosystems respond? What will happen to sediment and seasonal flows? And how will neighboring countries react? Whatever the answers, the Yarlung Tsangpo will continue its journey beyond the dam, connecting mountains, communities, ecosystems, and nations far downstream.